yesterday, and I mentioned that this was for the parameter set I that is termed Hopf, quote unquote, right? And we showed that the reason for that is, we talked about it yesterday. The reason for that is that there are two Hopf points, Hopf bifurcation points. So we'll talk more today about what it means to have a Hopf bifurcation point. I know that some of you already know what a Hopf point is or Hopf bifurcation is, but we'll discuss it a little more detail in this, at least to get from a qualitative point of view, so that you can get a flavor of what it is that's happening over here. What's going to happen at a Hopf bifurcation point is that a stable branch is going to become unstable, and a branch of periodic orbits is going to emerge from the passage from the point where the transition occurs, where you go from where the stable point becomes, where the equilibrium point becomes stable to unstable. From that, there will be a branch of periodic orbits. So I hope you can look at this picture and you can get a sense of what it means for a branch of periodic orbits to emerge from the Hopf bifurcation point. Okay. That being said, let's take a look at what happens if you pass through a Hopf bifurcation and a branch of periodic orbits occurs. There could be two ways in which this could happen. One way in which this could happen is the following. Suppose you go from a stable to an unstable fixed point regime in passing through the Hopf bifurcation. You could have that you get a branch of periodic orbits that appears like so. In passing from stable to unstable, the periodic orbits emerge on the side of the unstable branch, right? So this is like a crocodile mouth. If it opens up from the unstable to stable to unstable, you call this the supercritical Hopf. Okay. The other thing can also happen. The mouth of the crocodile can eat the stable branch itself. So when that happens, so this is a subcritical. When that happens, that's called a subcritical Hopf. Okay. So can you now tell me which kind of Hopf is this? Is this a supercritical or a subcritical? Subcritical, correct? And now this entire picture is mirror reversed. So can you tell me whether this is a sub or supercritical? This is also subcritical, because as you pass from the side of the stable to the unstable, the crocodile eats the stable branch. Crocodile mouth eats the stable branch. Okay. So this is a subcritical Hopf bifurcation. We also saw yesterday, I mentioned that these are periodic orbits that are unstable. Okay, and these are periodic orbits that are stable. So in a minute I will show you the phase plane that corresponds to these being stable and unstable. But let's just step back a minute. You have a question?
Sir, you can see that the critical point it was straight line.
This one 6.
So we have a stable fixed point and an unstable cycle.
Right.
So
unstable periodic orbit.
whenever we transform from a stable fixed point to stable limit cycle,
Okay.
the fact that there will always come an unstable limit cycle past.
I am not sure of the question. Maybe I'll describe this picture a little bit more, and then once we do the phase planes, you'll be able to answer that more carefully. I will show you a phase portrait of what happens in this region over here. I'm going to tell you in a minute that this region is a bistable region, and then you'll be able to see what is the meaning of having a stable fixed point and an unstable periodic orbit and a limit cycle, a stable limit cycle, all in one place, for the same value of the parameter. So let's get to that. But let's do it systematically. Let's look at this region over here, this broad region where you have green over here. What do you think happens over here? I showed you a simulation yesterday. If you start off at the fixed point is unstable. So any perturbation, whether you drive the perturbation by injecting a small current, or even if there is numerical instability simply because you're not calculating your codes to extremely high accuracy, whatever the reason, the moment there is a perturbation away from this, you diverge away from the fixed point to end up in this oscillatory regime, right? That was the canonical picture that we saw yesterday. Everyone okay with that? Alright, so let's look at three broad regions in this diagram. You've got a region in which you've got a stable fixed point, there's nothing else around it, no attractor around it, no other stable scenario possible, right? So in this region you will get attracted globally. This is not a local argument alone, this is a global argument. No matter where you start in phase space, you will get attracted into this fixed point over here. In this region over here also you get a fixed point. It's a different fixed point at a much higher level of V, okay, but you do get a fixed point over here. In this region over here, biologically you will see, or experimentally you will end up seeing oscillations. You will say, well, there is a fixed point. In principle you could be stationary over there, yes, but the moment you make a perturbation away, that because it's an unstable fixed point, you will migrate away from, the trajectory will migrate away from that fixed point. So in practice, where there are perturbations in the biological system, there will be noise, there will be all sorts of perturbation sources. No matter how much you try to damp them out, there will always be something that will jiggle your system. Or numerically you might have some numerical perturbations that are going on in your system. So in practice, experientially, you will watch the periodic orbit. The system will end up showing a periodic orbit. You should not believe that you have only the periodic orbit and therefore nothing else is possible. This example shows you that that expectation is in general not, you have to qualify that expectation a little bit. Yes, in practice, because of perturbations and so on, the only stable situation is the periodic orbit, but in principle there is an unstable fixed point which if you could delicately place your system at, you could be stable in. You're not stable, you could persist in. Does that make sense? Is that clear? Okay, so now that we've cleared this up, now I will show you a region in this, there are actually two regions in these, in this parameter space where the system can be stable in two different attractor states. Okay, let's take a look at this position. So I'm going to axis zoom on this region over here, and then you will start to see why I say that you could be stable in two different states. If you're at a position 5, right, that's a stable fixed point, and you diverge away from it a little bit, you perturb yourself away from it, because it's an attracting stable state, you will come back, the trajectories in the neighborhood of 5 will collapse back onto this fixed point. If your perturbation is large enough, what happens if you're actually stuck at this position over here? If you pick this position out, then that's an unstable periodic orbit. If you're exactly on an unstable periodic orbit, you will stay on it. But if there's a perturbation, you will move away from it. If you happen to be on this side, or if you make a perturbation and you happen to be on this side, whatever that means, you will get attracted towards the fixed point, because that's stable, that's attracting nearby trajectories. If you perturb and you happen to be on that side, whatever that means in a high dimensional system, but metaphorically if you're on that side, you will get attracted into the other attractor there is, the other stable attractor there is, right? The other regime that can attract you, and in this case it's an oscillation. So for the same value of the parameter, you've not changed I. Simply by where a perturbation leaves you, which means you're changing the initial conditions in a sense, depending on where the perturbation leaves you, you can get attracted into this or you can get attracted into that. So there are two attractors possible. One is stable fixed point, the other is an stable oscillation, and you can have either of those situations depending on where you start with. So in fact, you can also switch your attractor from one state to the other, and that's a very nice characterization of bistable systems, and it is often used in practice to check for bistability. You make a perturbation, a local perturbation, suppose you are stuck here, you make a local perturbation just to see that you are truly stable. So you make various local small perturbations, you find yourself getting attracted back to the state, and then you make a little bit larger perturbation without changing I. A little bit larger perturbation, you make it larger and larger and larger, and there will be two different things that will happen had you been stuck over here versus in the bistable region over here. In this, if you make a large enough perturbation, you might actually end up in the oscillatory state. Okay. and it can go the other way around also. In fact, you can also jump from the oscillatory state in principle to the stable fixed point, provided your perturbation is of the right type. When I say right type, it means that you should fall based on the you should have such a perturbation that you fall in the domain of attraction of the of that attractor. A domain of attraction is a notion that, excuse me, a domain of attraction is a notion that says what is the region around a particular attractor in which if trajectories start, they will get attracted to this fixed point or stable periodic orbit. Does that make sense? Okay. So there are regions. There's a domain of attraction. There's a region in which trajectories will get attracted to this. There's a domain of attraction for that, which says that if you start in that domain, in that region, you'll get attracted into the stable oscillation. Does that make sense? Okay. And a similar thing happens on the other side. When I say other side, I mean the other Hopf bifurcation. Axes fit. Okay. Any questions on this so far? So let's now look at the phase plane versions of these. So what we can do, or we will do now, is to grab various positions. In the bifurcation diagram, and we will see what their phase space counterparts are. Okay. So start thinking about what you might expect to see. So let's start with this position over 3, for example. Let's say I'm going to click on grab, and I found my cursor way down at the bottom, position 0. I'm going to use tab to move around. Let's say I'm at 3. I'm going to enter this position here. Now I'm going to switch to my phase plane, the WV phase plane. I'm going to plot, for example, an alkaline picture. Right now, everybody remembers the alkaline pictures from yesterday, so we recognize the alkalines. This is the V alkaline, that's the W alkaline. All right. Now, the particular value for which these alkalines have been plotted is the value of I corresponding to the point 3. That's an important point. Okay. This is not just an arbitrary drawing of the alkalines. I picked that point in my bifurcation plot. I picked the point 3, the I that corresponds to that, and in fact the trajectory location, meaning the V and W corresponding to the position 3, right, on the fixed point, on the stable fixed point, have been picked up and are available to XPP to plot. Okay. So in other words, I am grabbing that point, and the information of that point is known to XPP. So when you see the phase plane over here, you see the alkalines. Those are the alkalines that correspond to the position 3 in the bifurcation package. It is changed automatically. Yes, right. That's the lovely bit about grabbing it. Otherwise, I would have to set it up so that I change my so that I can find what the V and W are corresponding to the fixed point. Okay, and I find the I corresponding to that fixed point, the one which I'm interested in, and then I have to set up the I, and I have to set up the initial conditions to be that fixed, to correspond to the coordinates of the fixed point. Okay, those are the two things I would have to set it. But since this grab facility is available, those things are automatically transferred to XPP, which is nice, which is especially nice if you want to. Which is especially a nice feature of XPP auth, because that means that all of the precision that's available to you for the fixed point. When auto computes the fixed point, it computes it to a high degree of precision. In this case, it's a stable fixed point. So even if you make a slight mistake and you run trajectories from a point that is not truly a fixed point or not very close to the fixed point, but slightly away from it, it will still converge. The trajectories will converge to the true fixed point, so you can get away with it. But when you have an unstable fixed point in the bifurcation, then picking the coordinates exactly so will take a little bit of work. If you were to say migrate the information from XPP, use it in some other package, then you have to do that with a good amount of precision. You have to keep several decimals in place. Otherwise, you may be off the fixed point, and if you're off the fixed point, you won't find it. Any trajectory that is run from nearby will not be nearby any longer after integrating it, right? So it will make it becomes difficult to do it if you want to do it between packages. But in XPP and between auto, this thing is very streamlined. But you shouldn't forget that there is something in the background that's going on that's making your life easier. Okay. Okay. So I have this. Now let me plot my direction fields. Okay. Just the usual sort of language that we developed last time. I plot my direction vector fields. So as you might see, you can expect this is the kind of picture we saw yesterday also. You sort of tend to see a cycling of trajectories. We can check it. So let's check it. Yeah, that's the kind of picture we saw yesterday. Wonderful. Okay, great. So you have a fixed point over here. You can actually use XPP to find you stability of this. I won't show it to you here. Maybe I will. I don't know. I'm not sure. But it's a very straightforward piece of punching buttons and figuring out the stability of this fixed point. But in this case, we know that this is a stable fixed point because we already saw the bifurcation diagram and saw this was a stable fixed point. So I'm not going to bother doing it again in XPP over here. But know that you can. If you needed to, you could have found the stability by isolating this fixed point and asking XPP to return whether this point is stable or unstable. Okay.
So with the same point, we can use the same points.
Yeah, you will use sync points. That's correct. Yeah, play around with it. You'll see it. It's just a simple matter of punching keys. Okay, so we have this picture over here. I will come back to this picture a little bit later and I will show you certain interesting features of it. So keep it in mind. But now for the moment, I want to move to a different position in the phase space in the bifurcation diagram and ask what will happen if you were in a region where you had oscillations. So notice here that it does not seem like there is any way you can get a cycling going on. There's no way in which you can seem to have a periodic orbit. That just confirms what you saw in the bifurcation diagram previously. Is that reasonable? Right? With very small changes to the basic null line shape. I'm going to ask you to watch what the null lines do. Okay, the null lines will move relative to each other as I change I. Why do you think that is? Can anybody give me a reason why? What will happen if I change I to the null lines? Think of that. That's kind of the key in this analysis. If you change I, which equation does that affect? dv/dt, right? If the equation, let's get some chalk. Let's get this. So suppose you have dv/dt equals some f/v/w plus I. That's your applied current. IAPP, let's say, and dw/dt is some GVW. If I change I applied, it will affect this current, right? If it affects this current, and the null line is obtained by setting this equal to 0, the right hand side of the dv/dt equation equal to 0. So I apply is going to change the V null line, right? In what way will it change the null line? If I add I applied, will it? What would you think it will do to the null line? Correct. In which direction? Right. Fair. But what will, I'm asking, can you give me a global sense, not just of the intersection, but what happens to the null line itself? The V null line will change. It moves up. Correct. The V null line will change. So let's check this. The parameter I0 is 43.9. Let me make it something like 50. I've increased current a little bit and I'm going to redraw the null line. So the null line is lifted up. Okay, let me do that a little bit more. Okay, you can see the null line gets lifted up. If the null line gets lifted up, and you can convince yourself that that is what you expect by adding I0 over there. If the null line is lifted up, the position at which the two intersect is also going to change. Right? That's completely reasonable. Okay. So it's the relative position of the two null lines that changes, and that feature will change the kinds of behaviors you see in the system. Okay, that's pretty remarkable if you think about it. So let's now plot the phase plane phase portrait corresponding to being in the oscillatory region, and let's see what null line picture do you expect to find where you will get a periodic orbit. Ready? Okay, so let's do this. Let's grab this, and I hope this system will continue to function. Okay, I am over here, so I'm way deep into the oscillatory band with respect in the bifurcation diagram. I'm going to grab this, and let's hope that XPP will know to find this position. Okay, great. Let me. I want to change the viewports so that the rest of the null line, I don't want it, you know, running away. But I'll use a trick. What I'll do is since I'm on a trajectory. Remember, I picked the maximum and minimum. I know the trajectory also. Just like when I was over here at 3 back there at 3, I knew the coordinates of that fixed point. When I grab that position on the periodic orbit, I know the coordinates of being at the crest of that. I think it's the crest of the oscillation, right? So those coordinates are also available. So if I pick that and put it here and run, I should be on the limit cycle. I should actually be able to trace out a full curve. So I'm going to do that. I'm going to go do initial conditions, go, and I get a curve, right? And then I'll do a window zoom and zoom. Okay, hold on. Something's frozen up. Just give it a minute. There it is. Okay. So, does everyone understand why I got a circle? What the circle corresponds to? This circle corresponds to the periodic orbit that I had. I think I picked this point. The periodic orbit corresponding to this location, this parameter value of I, is what I am able to grab over here. Because I picked this point, I know the coordinates. If I run the trajectory corresponding to those coordinates, that gives me precisely the oscillation, but viewed in the phase plane. In the bifurcation diagram, I am able to see only the maximum and the minimum. In the phase plane, I am able to see the entire trajectory. Okay, does that help to understand? I still don't know what the direction of motion is, but I can get that very quickly. Do you think it's going clockwise or anti-clockwise? Is the trajectory moving clockwise or is it going anti-clockwise? Remember that I said in the phase plane you don't have time information available. You have to find an arrow and place it on your trajectories. How will you find it? By plotting the direction field, right? So let's plot the direction field. Now tell me, which direction do you think this is going in? Quick check. It is going anti-clockwise, correct? Okay, there you go. So it is going anti-clockwise because you see the vector fields are directed in that direction. You get nice vector fields which sort of say, oh look, it's going, things will move in to the right here, here, and so on. Once you pick out any one of them, you know that it's going anti-clockwise. So this is all very consistent. You don't have to do any calculations. You're able to work within XPP as long as you know what these structures mean for you. You're able to capture all of this in a very quick sense. You could have done all of this by doing analysis. Okay, there's nothing in particular here that I've shown you, but it will be a very tedious analysis, clearly, right? The way I look at it is, if once you a very convenient way to look at this is, once you look at these pictures and you sort of see what's going on, then you can confirm it with analysis, right? We won't have time to develop the analysis of it here, but this is a nice introduction, or this is a nice invitation for applied mathematicians to come in and now explain these things. Okay, does that make sense? Yes, you can get that information. You can go to that singular points block over here. You can, and it will tell you which fixed point you want to compute the eigenvalues of. Point to this, and it will give you a little box which shows you the eigenvalues. Okay, try it. If you need my help, I'll show it to you. What do you think the eigenvalues will be? Yeah, likely to be imaginary, or not imaginary. Okay, let's try it out. There you go. So it's an unstable point. Let's see if I can show you the full eigenvalue. There you go. Right? Can everyone read that? The eigenvalues are written in that corner over here. Okay. Does that make sense? Okay. So this point is clearly unstable. For those of you who know how to read eigenvalues to determine local stability. Okay, so that's what you have over there in the middle region over here, where you've got oscillations. What do you think will happen over here? Can anybody take a guess before we show the phase plane? Remember that the phase plane corresponding to, or at least actually look at this over here. There is a trend you can see in what is happening to the, I said it's the relative location of the two null lines. When you were over down there in the fixed point regime, the intersection was where? Along this n null line, the intersection lay here. As you moved into the oscillatory regime, the intersection is on the middle part of this n null line. And so extrapolating from this, let's guess that the intersection here will be when this null line moves up. If this null line is up there, this intersection will end up being over here. Okay, that is the guess, right? Just and because we can check it, let's do it. So let's go way over to 13. So 13 is up here. Let me grab this and look at the null lines corresponding. There you go. See, it has just moved past this is called a knee, like because of this metaphoric thing that I'm developing, this metaphoric language that I'm developing, this part of the null line, the middle part of the null line, the right side of the null line. So let's call this the right knee, and let's call this the left knee, the point of inflection where you go through 0 in the null line. Okay, so between the right knee and the left knee, now the position here has moved over to the right knee, and that's kind of interesting. And we'll use this idea a little bit later, but that's the sort of thing to notice over here. Okay, so we've got this null line. I'm going to erase the rest of the picture. Again, I'm going to draw my direction fields. The direction of motion hasn't changed. I'm sorry that this is the oscillation that corresponded to the previous case, right? I'm not going to worry too hard about how to get rid of it. Ignore it mentally. Let's just find another trajectory here. And if I look at this trajectory, look at all the trajectories in started from various regions in phase space, right? You find all of them. You find that they're winding around, but they're all eventually decaying away. So this is actually a fixed point. Right? The fixed point there and the fixed point here have different properties. They're both fixed points, but they have different properties. Okay, and one of the ways in which they are different is this intersection here is happening on the right. This thing part of the bit of the V null line that's after the right knee, and the intersection otherwise was happening down over there in the low I case. Okay, so that is our description of the phase plane dynamics of the Hopf variant of the Morris-Lacquard. So now I will tell you, are there any questions by the way? Does everyone see why as you keep increasing the current, you can jump from a stationary state to an oscillatory state? How this should be pretty straightforward to see. How would you do that? Why is this? Can you give me an explanation? Now that you know the bifurcation diagram, you have a good sense of the behaviors that are possible in the Morris-Lacquard Hopf regime, and you also know the corresponding phase plane portraits, so you sort of understand what's going on over here, right? And so I want to quickly check with you to ask, if you start your system at a low current, in which case it's in a fixed point regime, it's in a stationary stable state, and then you move into an oscillatory regime by increasing current. Can you explain that on the basis of the bifurcation diagram? What is happening?
So initially it was, if I just speak the mathematical, initially the stable equilibrium was stable mode. And then the oscillation comes, and finally it becomes stable spiral.
Yeah.
And if you put the current thing and something like that, when the current was small, low, okay, so then it was stable. Then after for a long current there was this type of shake, so that was probably the oscillation. And after that, if I increase the current so high that this oscillation, there will be nothing to oscillate.
Yeah.
So it almost something like giving someone top of very high voltage, so that it dies and becomes stable.
Yeah. Okay, fair enough. So what I wanted you to notice or think about is that if you look at the bifurcation diagram, you can pick out a current in the bifurcation diagram. At low values of the current, you got stationary state. When you increase that current, you simply move in your bifurcation diagram. You simply move to a new position in a higher in current, right? You move to the right in current because current is swept in the bifurcation diagram in that direction. So you can pick out if low current you have, what you might have a stationary state. If you have a slightly higher current, you end up in the oscillatory state, right? So that's a good way of deciding at how much current is required for you to switch from the silent to oscillatory, and how much current you can sustain before you switch back into the silent regime again. Okay, does that make sense? Okay, so it's a simple matter of deciding which position you are in the bifurcation diagram at. There are some subtleties that are associated with this. When I pull up the diagram again, I will show you some of those subtleties. But let me start you thinking about this. Suppose you are in an oscillatory regime, and you want to make sure that your neurons' oscillations are quenched. What maneuver will you do? What will you do to the neuron? Reduce current, increase current, or reduce current and then increase current, or increase current and then reduce. What maneuver of the current will you do so that you can achieve a particular effect? The neuron is oscillating under the application of a certain amount of current. I want to make sure that the neuron is silent. What is the maneuver you will do? The answer is a little bit subtle, so think about it before you answer. Okay, I want to make sure that the neuron is silent. Okay, yeah. Correct. Yeah. Yeah, fair enough. Okay, good answer. So let's. So she's saying, well, that should not be too difficult a question to answer. What I just asked you, you should simply move into a region given by a bifurcation diagram where your current is not oscillating. Fine, let's do that. So suppose you have, I'm going to try and draw this bifurcation diagram by hand. Okay, you've got unstable branches coming out, stable branches or periodic orbits, unstable branches. Yeah. Forgive me for not drawing it very carefully, but my chewed apple kind of diagram should be representative of the diagram that you've already seen. Okay, actually I'll turn on, thank you. Okay, so if you find yourself at this position in the current, in the applied current, right, and you're oscillating, and my question was, well, how do you make sure that this, what do you do, what maneuver do you do to make sure that this is no longer oscillating, that it is silent? Well, she says you can simply lower your current to find yourself in a region where you will no longer have oscillations, in which case whatever oscillations you started off with will eventually die. You wait a little bit long, you wait long enough, and eventually you will find stationarity, which is what the bifurcation diagram predicts. Okay, great. Now suppose I ask you, I want to be in a bistable region. I want my current to be this. And the first question I'll ask you is, starting from here, how do I make sure that the neuron doesn't spike? And starting from here, from that position over here, that's my I0 position, I start position. I want to move it down to this position, to this IB region, to that current, but now I want my neuron to oscillate. What do I do? Just a quick test on whatever things we've seen before. Anybody want to give me an answer? You can't control the initial values. This is an experiment you're doing. You don't have exquisite control over the initial values because the gating variable you can't change. You might be able to do a current clamp to change the voltage, but you have no control over what the gating variable will be. Correct? But I don't know the basis of attraction. I'm doing a physical experiment. You've done the mathematics. You've gone to your biology collaborator who can do the experiment for you. What experiment do you suggest? That's the role of the mathematical biologist. You should suggest, look, I find that there is a bistable region in this system. So experiment says, that's awesome, I will check it for you. You say, oh, design that experiment for me. What did you want me to do? I will do it. And then you say, well, here's what I want you to do. So what do you want them to do? Resonance frequency. No.
So we can tell them that just increase the value, the initial value.
What initial value? I0. Your injected current is I0 to begin with. The first answer was correct, that you can switch to let's call this L, to find a stationary position, but I would like to find the bistable region, in which case I would like to design an experiment so that I land up at IB. I know the value of IB because my simulation shows. I need to go to my collaborator and say, well, do this an experiment, and at IB you will see that there is a bistability. So I need to show the experimentalist that if you switch it, if you do this, then you will find a stable state. If you do this, you will find an oscillatory state, both at the same value of IB. IB. I want to eventually be in IB because that's where my bistable region is. So I need to design a suite of experiments so that I can show stationary state at IB and so that I can show oscillatory state at IB. I need to be able to achieve both. I want to be very close to IB, which is possible to do because I have a way, or the experimentalist has a way of tuning the amount of current they've applied. So,
want to maintain the current in particular value so that it won't go beyond that.
That's not the mathematician's concern. How to maintain the value at a particular value of the current will be determined by the experimenter. They will put in their negative feedback amplifiers and this and that and maintain the current at whatever value you ask them. But my point is, at the value of IB you could have an oscillation, at the value of IB you could have a stationary state. I don't want you to guess. I want you to design a protocol so that you will find an oscillatory state at IB. When you end up at IB, you'll be in an oscillatory state, and then another protocol in which when you end up at IB, you will be in a stationary state. That you design for me. Anybody want to guess? Sum together whatever I've said for the last half an hour. Okay, let me see if you agree with this. Anybody want to suggest something before I give you a possibility, a possible answer? So then you're guessing. That is correct. That would be the naive approach. Change. You move to IB, stay there, and then try to change conditions somehow by picking different values of the current or by picking different values of the voltage and so on, in the hope that you will manipulate it. In some cases you might find oscillation, in some cases you might find stationary states. That's the trial and error brute force approach to it. Yes. What if I say that you could design a systematic protocol that you will find this in systematically? Okay, here's this. Okay, so tomorrow try doing this experiment in the tutorial. Okay, let's design this, or maybe I should wait until tomorrow to give you the answer. No, I'll give you the answer. Here's, try this tomorrow in the tutorial. Okay, start with I0, drop it all the way down to IL. You for sure will have a stationary solution. Now start increasing the I slowly. That I claim will guarantee that you will stay close to this. Why? You increase it slowly from IL. You can increase it slowly all the way up to IB and find yourself in this position. Why? Because any perturbation that occurs by moving your current, by changing your current, will be, if you move it small enough and you control things carefully enough, it will be small. And this is an attractor state, this is an attracting fixed point. So any perturbation that there will be damped and you will go back to the moment you move over here. Maybe there's a perturbation that's introduced because you moved over here, you're over here, you moved your current, so you're slightly away, but this is an attractor state, so you can clamp over there. And you can do that slowly. The reason I'm saying slowly is so that the perturbations aren't large enough. When you do that slowly enough, you will track this this branch entirely. Then finally you will be in the position IB. And there you go. You found your fixed point. You found your stable state, your stationary state at IB. Now do another thing. Add pulses to it. You're at your tonic. Your tonic amount of current is IB. You found your stable state. Now add a pulse riding on top of it. So you got your IB, apply it, add a pulse. When you add a pulse to it, it will be a perturbation. The perturbation will kick you off. If the perturbation is small enough, you will return. As you keep on increasing the perturbation, the size of the perturbation, the amplitude of the perturbation, at some point you might switch the domain of attraction. You're likely to switch the domain of attraction. At some point you jump here and then you will start seeing oscillations. So for that, you haven't changed I, you haven't changed the basal current, because the perturbation always returns back to 0. But the effect of the perturbation, the effect of the pulse will be to maintain IB. You will maintain IB, but you will see oscillations in this region over there. So that would be a protocol that I would guess should work, and you should try it out in your simulations now that you'll have the facilities to do it, to see if you can do it. Maybe the experimentalist can do it as well. Okay, does that make sense? Okay. Alright, so let's now switch gears a little bit and talk about the other mode in which ML can operate, that is to say, a different set of parameters that have been found to place the Morrison car in a different regime. We saw that for the Hopf regime of oscillations, we saw that oscillations emerged essentially from there being a Hopf bifurcation, from the fact that there is a way from the fact that there is a Hopf bifurcation, in which case as you lost stability of the fixed point, you had a branch of unstable periodic orbits emerge, right? Okay, it's a little bit subtle why the Hopf bifurcation is giving rise to an orbit, or is giving rise to a periodic orbit, but essentially, and the subtlety arises from the fact that if you move in this direction and you pass through and move to this position, well, you're getting attracted to this periodic orbit. That's the stable attractor over there, whereas the Hopf bifurcation is saying that the branch of periodic orbits that emerged was actually unstable. It may have been unstable, that's okay, but if you did follow this branch and you were perturbed away from this branch, there was also a globally stable periodic orbit that was there, right? So you would switch into that orbit. So I think it's fair to say that essentially the Hopf bifurcation structure, together with the presence of a stable periodic orbit that is away from the fixed point, is giving rise to oscillations in this model. And the oscillation essentially arose from the Hopf bifurcation arising in the phase plane version because of the relative location, the relative positions of the Nath lines, right? I will show you now another mode, another means by which you can get oscillations in the system. And in this case, the phase plane structure is going to be different from the phase plane structure that we saw for the Hopf regime. Okay, but first let's do the bifurcation diagram, and you will see that the bifurcation diagram also looks different from the Hopf regime. So we will call this regime the SNCC regime, the SNCC mode of operation, that new mode. This was called the Hopf mode, and that other mode is going to be called the SNCC mode. Now I should say at this point that these two modes, which we are looking at from a mathematical point of view, actually correspond to differences in the behavior of neurons that had been observed previously. Before this explanation was given, I believe it was John Renzel and Bard Ermentrout who gave these explanations of what were called type 1 and type 2 neurons. So there is a type 1 behavior of a neuron, there is a type 2 behavior of the neuron, and what Renzel and Ermentrout showed that the type 2 behavior was essentially arising out of a Hopf pattern of bifurcations, or Hopf bifurcations leading to oscillations, and type 1 neuron behavior was arising out of a SNCC pattern of bifurcations. Okay, so we'll talk about what the SNCC bifurcation is, and then we will go back and show what experimentalists had seen in terms of type 1 and type 2 behavior, and then we will match it with the behavior that you expect from having these kinds of bifurcation diagrams. Does that make sense? That's the program here. Okay, so I'm going to tie in, even though I'm starting from the mathematics of it, showing you the analysis and so on, the mathematics has a purpose. The mathematics is there to explain that the type 1, type 2 behaviors neuroscientists have seen in experiment map nicely to the properties of the Hopf regime and the SNCC regime, these two bifurcation scenarios that arise very naturally in these systems. Does that make sense? Okay, so one will map onto the other. We'll be able to understand one in terms of the other. Okay. So SNCC regime will be called type 1 and Hopf regime will be called type 2 to mirror the type 1 and type 2 behavior that was seen in experiments. Alright, so let's, I have to start the X server. Actually, what I'll do is I'll take a short 2-minute break and I'll come back and we'll discuss. Okay. Take the question again, and this time I will pick the parameter set correspond to SNIC. So this file is set up very nicely by Bard, where you can pick the two parameter sets without having to set them separately into separate files and so on. Okay, now let's take a look at the null client picture. What do you notice about the null client picture? And I believe this is at I0 being 0. Is there anything subtly different that you find about the null client picture relative to the? Yeah, so a lot of you have seemed to notice that there are actually 3 points of intersection, not 2. Okay, and it is not terribly hard to see why that could have been. That is happening because this null line, which went like so, is now oriented like so. Okay, so by a change in the position, in the relative positions of the null lines, and by maybe moving the null lines, changing their shape slightly, you get to have 3 intersections of the two null lines without changing the basic shape of the null lines. When I say you're not changing the basic shape of the null line, obviously the details vary. However, the fact that this is sort of an N-shaped null line, it's a cubic null line, and this is sort of a monotone increasing, maybe sigmoidal kind of graph, that basic pattern isn't changed. And this is an extremely important point that I would like to make over here, that when one studies the qualitative behavior of differential equations, it matters to us not so much what the exact parameter values are and so on. What matters to us is what the shapes of the null lines are. It is the shape of the null line that is actually that carries the gem of the idea, the essence of the idea. This is an idea that is often used for making models as well. For those of you who are interested in building models, there are three aspects of modeling that typically form the modeling lifestyle, the mathematical biology lifestyle. One is you make a mathematical model based on some data or some experiment that you would like to explain, some biological process that you would like to explain. So that's the model construction bit, right? And then as an applied mathematician, you go in and then you analyze it, you figure out ways in which you look at those equations, you can run simulations, and then you do the analysis, maybe of the type that we are doing over here, the geometric analysis point of view. But you try and figure out what those equations can do, and if you were to change things, what these equations might do differently, and so on. In particular, if you're studying, for example, you would want to study, for example, what happens as a parameter, in this case the applied current, a physiologically reasonable, a physiologically interesting object, as it is changed systematically, how the behavior of the neuron will change. Okay, so those are the sorts of questions that an applied mathematician asks. And then once you come up with a prediction, once you come up with interesting features that you would like to test in experiments, you take it to your biologist collaborator. Hopefully you have found an experimentalist collaborator. You take it to them and say, well, if you were to design such and such protocol, which I see based on looking at my bifurcation diagram or my analysis, then please carry it out and tell me whether I'm right or wrong. If you're right, great, you move on to the next thing. If you're wrong, back to the drawing board. You have more interesting problems to solve. All right, so that is the whole model, analyze, predict life cycle of modeling in mathematical biology. All right, so now we are in this process of we've gone to the model, we're analyzing it. So in the analysis, let's say you've come across this behavior and you say, oh wow, there are 3 points of intersection, which you sit back and say, is that natural? Yes, it is natural, because it is only dependent on the shapes of the null lines, and you can orient 2 different curves to intersect in more than one place. You can, for example, imagine a scenario where by altering your null lines, you might get an intersection that looks like this, right? And so in fact, try it out in your when you're playing around with these things. Set up, vary parameters in such manner, just keep playing with parameters until you find what you're looking for. What you're looking for is an orientation of these 2 null lines such that you get a null line to go like this. You get the green null line to pass through here. Okay, so it's an interesting question. What do you think will happen over there? Okay, I'm going to leave the answer to you. It's an exercise for you to think about. But I mention it because you might ask, what else can I do with these 2 null lines? And I'm giving you an answer to that. Well, here's one thing that you might do. Would that be interesting or not? I'll leave it to you to figure out. I will show you a situation where the intersection on this side, there's an intersection on the left branch. I'm going to call this the left branch, the right branch, and the middle branch, right? The left knee, the right knee, and middle branch, left branch, right branch, just so we have a language to talk about. In this case, there's an intersection of the W null line on the left branch and 2 intersections on the middle branch. Okay, now let's quickly go in with XPP, since I've already shown you that you can do singular points analysis with this. If I go click on this, let's print the eigenvalues, because some of you would like to see what the eigenvalues are. Let's not print the invariant manifolds. This is a stable position of it. It says right over there, and it's consistent with the eigenvalue structure. So this is a stable point. Okay, let's do this again and pick it over here. Let's do mouse, click on the guess. My guess is to have something around here. Eigenvalues, yes. No invariant sets, and this is an unstable. So it turns out that the middle of these 2, when I say middle, I mean this one, this triangle one. This triangle singular point is actually an unstable point. So this is a stable point, that's an unstable point. What do you think that might be? Take a guess. Half of you can say stable, the other half you can say unstable, some of you will be right. The question is, which camp are you going to be in? So let's find out, okay? Click on guess. I'm going to click over here, print the eigenvalues, yes, and there you go, that's your answer. It turns out to be unstable. Okay, great. So let's figure out what this is. Okay, so now we can move things around. If I add a current, what do you think the current will do to this? if I add a current to this, if I increase my current, my applied current, what will happen to the null clines in general, and what will happen to the fixed points? Take a guess. The null cline, this V null cline will start getting raised, right? If you raise it a little bit, you will not change the location of the fixed points, the stability even maybe. But if you raise it quite a bit, something new and dramatic can happen, right? Can you think what might happen? Okay, so I leave it to you to think. Let's plot the bifurcation diagram. Okay, all right. So I'm going to start with being here. Let's pick. I need to run a bifurcation diagram, so I'm going to start here, and I'm going to do IL a couple of times. Okay, that's what that flashy thing was, and I'm going to switch to auto. Okay, and my parameter is going to be I0. Let's confirm that. Yes, it is. I'm going to take axes, high low. Yes, okay. Numerics, I'm going to increase the number n max just because I can. I'm going to make the parameter min minus say 100, and I'll tell you in a minute why I did that. Let's make this 250. Okay, the reason I make this minus 100 will be clear in a minute once I do this. Okay, I don't mean to run my current negative. I don't mean to apply negative current, but you'll see in a minute why I need this. Okay, I've done this before, so I think in the interest of time I'll just use my insight. Let's run the steady state. Okay, and then hopefully axis fit will do it. Yeah, there you go. Okay, so now you see a very interesting picture. Okay, remember what you saw for the Hopf regime, the type 2 neuron. You saw the steady states, started out by being stationary, then they became unstationary, then they became unstable, and there was some lumpiness, some rippling around, but essentially the curve went right through like so, right? Here there's a very interesting behavior. You go up, then the curve turns around and goes back, right? This is the curve of stationary points. It is stable till here, and then the same curve continues. It's still a branch of fixed points, but they become unstable, and the curve moves backwards in the parameter direction. And in fact, it turns around once more and turns forward, and now it becomes stationary. So now you might think, well, now how am I going to get oscillations? First of all, let's take a quick check whether this is consistent with the phase plane picture that we drew. In the phase plane picture, we are starting here. This is zero current, right? Remember that I showed you had one stable point and two unstable points. So what do you think this point is in the phase space picture? Which intersection was this point? So in the phase space picture, corresponding to this position, is it this point or that point or that point? Which one is represented by that red dot? Left side, correct. It's the one over here, right? And these are the two unstable positions, so they are likely to be middle branch and right branch. Sorry, not middle and right, but the middle and the upper middle, correct, respectively. Right. So when you get to do your tutorial, just want to confirm these things. Right. Raise hypotheses like these and ask, is this correct? And you can go back and check. Right. I could do this for you, but I'd like you to try it. Okay. So that's the one stable and two unstables. Great. This is nice. This is interesting. We didn't seem to see any of this in the Hopf bifurcation. So this is a completely new behavior. In the type 2 neuron, we didn't see this. In the type 1 neuron, we are seeing something genuinely fundamentally different. Is that convincing? Is that am I convincing you that the qualitative picture for the type 1 neuron is fundamentally in some ways different from the type 2 picture? There's something genuinely new that's happening over here. So I say there's a qualitative difference in the type 1 and type 2 neurons. Now, to reiterate my previous point, I might be able to change parameters of the neuron other than I might be able to change some of the conductances, maybe the EK is not quite minus 74, maybe it's minus 72 or something like that. I may be able to change those things, and maybe those things don't affect the general picture as we are describing in the qualitative sense. You might find the same sort of null-line picture even if you were to change, for example, the EK a little bit or the GK a little bit. So that's another thing that applied mathematicians love to do. You vary some of the parameters and ask in which cases do the qualitative pictures look the same and in which cases the pictures look qualitatively different. So you develop an intuition for what qualitatively difference means. And I'm trying to help you get to that point in showing you these major differences that exist between the type 1 and type 2 neurons. So I hope you will agree with me that this is a major difference between the type 1 and type 2. Okay, so this point over here is called the fold point, and Otto also knows how to find it, and it will be called an LP in the Otto language. Okay, this is a position that's marked as LP, and in fact if you go up there, 7, check it for yourself, will also be called an LP. Or why don't I do it? Okay, there it is, it's also called an LP. So let me, if I'm over here, it will be LP. What do you think that point might be? Is it going to be a fold point? You see, you can recognize the fold point from the bifurcation picture, right? There's a folding of the branch here. There's a folding of the branch over here. It's an illustrative, metaphorically evocative name that the branch folds around. Okay. What do you think this point is? Anybody want to guess? Do you think it would be a fold point? Do you want to suggest something from something you've previously seen? Maybe a Hopf point, right? So Hopf points also have these properties. Let's ask if Otto if it's a Hopf point. Tap 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 tap. Okay. Yes, indeed. Point 12 is actually a Hopf point. So what do you expect to happen at 12? What you expect to happen is, if I were to, that's right, that we've already seen over here. What else, what other structure is there nearby that I have not yet computed but you expect to find, given that it's a Hopf point? You expect to see a limit cycle, right? So good. So let's find out limit cycle. Let's click on enter. I have grabbed this and I'll go to numerics, and just to be a little bit careful, I will change the sign ds to minus. Do you think you see what ds might mean?
So it will show the bifurcation backwards.
Yeah, so if I, not bifurcation backwards, but I will sweep to the left in decreasing directions of I0. If ds is positive, I sweep to the right. If ds is negative, I sweep to the left. Negative this direction, positive in this direction, so it will sweep to the left. So I don't know this, I'm not supposed to know it, but I will try plus and then I will try minus. I think I know that minus will work better in this case, so I'm going to try minus. Okay, just to, in terms of what you should take away from it is, you could have done a minus. So here is an example where minus might work. Okay, so now I go to run and I should ask for periodics, right? Because I expect to have periodics emerging from the Hopf point. Okay, there you go. So you see this. Okay, axes fit. So you notice something that I thought that it might turn out to be a supercritical and branches will come out like that, but no, it actually turned out to be subcritical and branches came out, unstable periodic orbits came out of this. Everybody recognize this as a subcritical, right? Okay, so my expectation of having ds being negative is not met, but the cool thing is that even though I set my ds to be negative, that means I was trying to sweep in this direction. Otto was clever enough to know that the branch of periodic orbits is if you sweep to the right to begin with. Okay, so that's nice. That's a nice feature about Otto, that you will be able to run the branches in either direction, regardless of the direction you think the branches are going to appear. Okay, so Otto shows that there's a branch of unstable periodic orbits, which at 21, this value of I0 will turn around to become a branch of stable periodic orbits. And then something messy goes on over here. This actually is a little bit of a numerical artifact, so we'll ignore that for why this is turning blue and so on. I'm telling you that's an artifact, but you can also recognize it that something not very consistent is happening over here. But given that you're able to ignore this this numerical artifact, let's ask ourselves the question that we asked in the Hopf case: how do oscillations emerge in this system, right? We went through a series of subdividing, we went through a series of subdivisions of that question, how this will happen, if that will happen, and that so. So let's ask those same questions over here. How do you think oscillation is emerging over here? Are there features of the bifurcation diagram that we do recognize? At least some of them are. What kinds of features do we recognize from the Hopf scenario? Well, the stuff over here, right? This stuff we seem to recognize. That's the kind of stuff that we saw previously as well. What we don't recognize, what is different, what is new, is this stuff over here. That bit is new. So we need to ask ourselves what is happening over here. Anybody want to suggest what might be going on over here? Something very strange seems to be going on, right? And we need to explore this. This is the thinking of an applied mathematician. Well, I don't see that structure recognized as being recognizable. So I would like to explain this, explore this, what is going on over here. Clearly, this branch that was coming out, poof, dies in the midair. What is happening to this branch? It's a homoclinic bifurcation, right? For those who have not seen this before, what do you think is happening here? Tell me what you intuit by looking into this. I'm asking you to just simply take a look and take a guess. What do you think is happening as you pass from here to here? If you are here, what do you think will happen? You'll be stationary, right? Because there's only one stable attractor. If you're over here, you will be oscillatory, and that's the only stable attractor. So modulo perturbations, that's the only thing you will be able to find. You won't be able to find the unstable attractor. And there is a passage in going from here to here, from stationary point to oscillation. So how did that passage take place? What is the behavior that is taking place in going across? That's the question I'm asking you. That's what I want to motivate and then describe later, right? Because yeah, this part I understand now. I've already seen this sort of structure behavior, so I think I know what's going on over here, right? That's my bistable region. There's going to be an unstable periodic orbit over here and a stable limit cycle over there, and they will envelop the stable fixed point. Okay, but I'd like to understand this bit. So so can you suggest what I might do? What kind of experiment with XPP I should do to figure this out? Well, the experiment is straightforward. I'll try and plot the phase plane, right? I will plot the phase plane corresponding to this position, and I will plot the phase plane corresponding to that position, and then by changing I in between, I will try to see how I went from here to here. That's what I will do. Correct? Does that make sense? That's a way of saying phase planes are very important, very interesting. You can see the bifurcation diagram. It tells you what the map of the activity is. It gives you a map of the activity with changing I, but doesn't tell you what mechanism is causing it. And then for a mathematician, the mechanism is how did this passage take place. You can hypothesize that in changing the I will raise the V null line, and the location of the fixed point will move. And that is what is giving rise to the fixed point, to the passage to oscillations. That's what we did for the Hopf. Do you think it will be different here? That is what I mean by asking what is the mathematical mechanism behind why this happens. Do you think it will be the same? Remember the Hopf position picture? We saw that the relative location of the fixed point was changing along the branches. Do you think that is the kind of mechanism that will happen here also? How many people say yes? The question is a little bit more subtle than I made it sound, but of course, if you change the relative location, then the fixed points will move around. But I'm asking whether it's the location of the fixed point that passes through is the mechanism by which this oscillation is emerging. Nobody wants to take a guess? Nobody wants to say yes? That would be the obvious hypothesis to try out, right? Yeah, but you're all too smart. You don't think that's going to happen, right? Maybe I've preempted the answer. Okay, let's go find out. Okay, let's start with 2, and let's look at this position over. Let's look at that in the null line. Okay, this location over here. So I is 19.79 for this position 2. I think. Yeah. Yes. Okay, and this position over here 10 or so is when I has moved to 50. Okay, so I'm going to start with this position over here. Let me grab this again. I'm going to start with 2, which is on the order of about 19 or so. Its bifurcation diagram, its null line picture looks like this. And just to give you the direction fields, those direction fields also look like that. We've seen this picture before. Everything will go sweep around and come to this. We've seen this before. Okay. Now I will switch to the picture in which we are in the oscillatory regime. So I will change Pi0 from this to say 50. And let's see. Okay. Make your own mental guesses. What do you think will happen? There it is. Okay. Everybody saw that this moved up. Yeah. And what happened? How many fixed points do you have? One fixed point. Correct? Which is not unexpected given that you're over here where you expect to see only one fixed point. Okay, so that was not unexpected. You knew that from the bifurcation diagram, right? What you need to look at also, what you need to confirm in this phase plane picture is, if I look at the direction fields, I should be able to spot a periodic orbit. So that's the direction field. There's a periodic orbit in here somewhere. I can do it in two ways. I can go and grab the periodic orbit for the corresponding point in auto, and then try and just run it here. Or I can do the other thing. I can start from some initial condition and hope that will come close to the fixed point. Why do I close to the periodic orbit? Why do I expect that? First, two questions here. One, tell me what initial condition I should start my trajectory at, and why do I expect it at all to come closer to the periodic orbit, to the limit cycle that is there in the system at this value of pi. I know that there is a limit cycle in this because I saw it in the bifurcation diagram. I'm looking at, I want to find it here, and I'm saying the easiest thing to do is to find an initial conditions from which if you start, you will come closer and closer to the periodic orbit. Why do I expect that? It's a stable limit cycle. There is no other attractor. There's a fixed point attractor there. There's a fixed point there, but that's unstable. So no matter where I start, that's the only one I should be able to. So what initial condition should I start with? You can start with any, right? Let's see if that is true. Okay. Are you starting to see where the limit cycle is? Are you spotting where the limit cycle is in this? Okay. Right? Okay, so the limit cycle is, it's this guy over here. Right? You want to see it more carefully? Okay, I'll show it to you more carefully. Okay, I will do initial condition last. Okay, there it is. I did initial condition last means what is happening over here, to be precise about it, is I started from some arbitrary initial condition. This is an attracting periodic orbit, and I know that that's the only global attractor, so I anticipate that it will attract all trajectories in this phase space, and that's exactly what I found. I saw this trajectory becoming closer and closer to the limit cycle. So I start with initial condition last, in which case I lose the transient information, and when I'm already close to the limit cycle, I run forward. Then this curve appears. This curve means that I am really, really close to the true limit cycle. If I plotted it from auto, if I grabbed the limit cycle from auto, then I'd be even more accurately close onto the limit cycle. But this, for all practical purposes, is already very close to the limit cycle. The limit cycle, notice that you will never land up on the limit cycle unless you start there, but you can become very close to it if it's an attracting limit, if it's an attracting periodic orbit. Okay, a stable periodic orbit. So that's what's going on over here. We have found ourselves the limit cycle in this system. Okay. Now, my last piece of the puzzle. How did I pass through the critical zone? The fold point seems to be the critical area to land up. Oh no, I will have to do this again. Sad. Let me do this again. Let me start it again. By the way, you can save bifurcation diagrams in XPP, so you don't have to compute them over and over again. But it won't take too long, so we'll just continue it. We'll just plot it again. You bear with me a minute and we'll do it. We'll get there. By the way, now do you realize why I set this to parameter maximum to minimum to -50? Because the fold point was taking me to negative values. Then I needed to be able to compute it. If I set it to 0, it would stop computing. I needed to turn around. Okay, there it is. Okay, so where was I? Right, we were describing transitions across here. So we described the phase portrait over there. We described the phase portrait over there, and you saw that this was related. And in the phase portraits, you saw that when you were plotting the phase portrait over here, you saw 3 fixed points. When you over here, you see only 1 fixed point. Okay, I want that to be a clue for you to decide what might be happening over here. In a minute, I'll show you what it is. Okay, so we can do that experiment here. Anybody want to suggest how the fact that you've gone from 3 fixed points to 1 fixed point could be the reason why your limit cycle is appearing? Okay. Yeah, right. Okay, fine. Yeah, that's correct. So it is a saddle node bifurcation. So here's what's going on. Let's start with Pi0 being 20. But I want you to tell me what is happening in the phase plane picture. What exactly is going on? That's my intuition. Okay, so I'm going to increase I0. What do you think will happen? Okay. All right. So let's start and move this to 25. Okay, replot it. So the blue null, the red null line is moving up. Let's make it 35, and it has moved up again. Okay, so what is happening in terms of the fixed points? Can you see some pattern emerging relative to the I is equal to 20 where you started? These two fixed points are coming closer and closer together. Okay, watch this once more. I0 40. See, let's see what happens. These two, there are two fixed points, except that they become very, very close to each other. And now if I raise my null line even past this, these two fixed points will disappear. You can't have an intersection anymore because the curve will lie above here. The only point of intersection can lie over there. So these two fixed points, which started out here and here, one of them stable, this one stable, this one unstable, are coming closer and closer together simply because of the location of the because the red null line is being raised relative to the green null line. The green null line is in its position because the red null line is rising and rising. It becomes harder and harder for these two fixed points I mean, they come closer and closer, and finally, as beyond a certain critical value, these two fixed points will disappear. So let's see 45, and the fixed points have disappeared. Correct? Now you can see right from the null line picture itself, there is no way there's an intersection here. Okay, the only intersection is over here, and that corresponds to the bifurcation diagram as well. As you're moving across, you have 3 fixed points, and so this point, this fold point, must correspond to that very critical position where the two have touched each other, right? And beyond that, boom, they vanish because that point is not a point of intersection anymore. Right? There's no way you can get 3, and that's when you are in this region over here, right? So the passage through this zone is by losing two fixed points to one fixed point, and since you're losing an unstable and a stable position, and only the third unstable remains, in which case I mean you're losing a stable and an unstable, and the only and this upper unstable remains. This kind of bifurcation is called a saddle node bifurcation. Okay, so that pinches off. These two fixed points come together and pinch off. That's called a saddle node bifurcation. And you will now this is unstable, right? So the question you will have in your minds is, well, if this is unstable, what else is there for me to find in a stable manner? So for that, let's plot the direction field. And what might you find? Well, look at this. The direction fields are going like so. You're turning around, going, and something happens here which I'm not quite able to see. But if I were here, I would go up there and go down here. But then if I were here, I would go up here. So something is happening over here in this region over here, but there is no way to be stable over here, right? There is nowhere you can actually land into a fixed point and say, ah, that's what they were headed for. Okay, so let's see what happens. Let's plot a trajectory over here. See, so what is happening actually is that this gap that is created allows for trajectories to pass right through here, and the trajectories seem to be coming right through, going all the way around, turning, coming back into the funnel and passing right through. So that means there's a periodic orbit over here. Okay, so that's why this is called sorry, let me just show you this picture over here. What is happening is, as the saddle node bifurcation occurs and the saddle and the node pinch off, what appears in its place is a periodic orbit. So that's why this is called a snake bifurcation. My chalk, oh, here it is. A saddle node bifurcation with the appearance of an invariant circle, SNCC, or sometimes people call it sniper bifurcation. A saddle node bifurcation with a periodic orbit that emerges in its place. So a periodic orbit emerges at the same time that the saddle node occurs. Notice that the saddle node is a local bifurcation. That is the picture which you can understand by looking in this region over here, and you don't care about anything else, right? The appearance of the periodic orbit is a global phenomenon. It's a global feature. It is a feature of this nullline turning around, there being flow here which allows this periodic orbit to emerge. So in the bifurcation picture, what you find is, as you pass through the saddle node bifurcation, a local bifurcation, as you pass through the bifurcation, what appears instead, appears in its place is a periodic orbit emerges at exactly the position where this bifurcation occurred. And I want you to think about why, and I want you to think of that explanation as the reason why this branch comes and vanishes into midair. Okay? And some of you mentioned that there's a homoclinic in here. So a homoclinic, you can discuss with me afterwards what a homoclinic is and why this is interesting and so on in its own right. That's a special mathematical logic. But that's what's happening. You're losing two fixed points to a saddle node bifurcation, and the moment you lose it, a periodic orbit appears in its place. It's as if the periodic orbit is prevented from appearing in this region because you had three fixed points, and that's a reasonable way of looking at it, right? And the moment these two disappear, boom, the periodic orbit shows up. So that's why it's called a SNCC bifurcation, saddle node and an invariant circle. Notice that the saddle node component of it is a local bifurcation phenomenon. The invariant circle is a global feature of the phase dynamics. Okay? So it's a mixture of a local and global phenomena. But nonetheless, this is a very canonical generic mechanism for how oscillations appear in biological systems. This picture now takes you away from necessarily having been stuck with neuronal systems alone. These kinds of pictures actually happen in many situations in biology. So these are ideas you can carry over from neuroscience to other aspects of biology as well, right? So the saddle node bifurcation and Hopf bifurcation are what are called generic codimension 1 bifurcations. Right? For remember this name, and if you want to discuss it with me, we can discuss it. If you come across this in your reading, you will know what these things are. And these are what that basically means is that these are the two bifurcations you would look for most commonly occurring in natural physical systems as you vary one parameter. So codimension 1 bifurcation, these are the two ones that arise naturally, and I've shown you a real example where these two bifurcations occur with different parameter sets in the Morris-Lacar system. Okay, so in the tutorial tomorrow, what I'm going to do is I'm going to list a few properties of the type 1 and type 2 neurons that were known experimentally before this bifurcation picture was posed as an aha to explain why these features were there, right? And in the tutorial tomorrow, we will explore how these bifurcations, the saddle node and invariant circle, the Hopf bifurcation, actually gives rise to features that were experimentally observed, in fact, before the explanation came. Okay, does that make sense? And I will also give you a little bit of a tutorial, I'll give you a tutorial question on also how now you might look at coupling various neurons and asking, what if you had not just one neuron but two neurons and they were communicating, what kind of patterns might emerge from these two talking to each other, right? So I'll give you a little question there as well. This is a very vast field, lots of interesting mathematics over here, so which is why it has attracted the attention of applied mathematicians for many decades now, and there are entire books that are written on it and so on. And if you'd like to get started on it, then the place I recommend is the book by Ermentrout and Terman. This is one of my favorite books for understanding some of these things. But if you'd like to write to me for other references, there are books by Izikevich and so on, where bifurcations have been dealt with in much more detail. I should also say that we've not formally covered a feature, an aspect of neuroscience called bursting, but bursting is this idea where if this is an action potential, what if you had a train of action potentials and then they became silent again? Okay, and then they started firing again and silent again. This thing is called a bursting. You've got a burst of action potentials followed by a silent phase, and then a burst of action potentials followed by another silent phase. So an active phase of lots of and a silent phase with no activity and so on and so forth. This pattern is called a bursting pattern. Bursting patterns have been very well studied as well, and there's a lot of literature on studying bursting patterns. I know a lot of people study Hindmarsh-Rose neurons. And Morris-Lacar is actually a canonical example that has been used to study bursting patterns. You might get into that literature if you like to. There's something called relaxation oscillators. Lots of physicists enjoy working with relaxation oscillators. Morris-Lacar, Fujinagumo, these are all canonical relaxation oscillators, or actually they can be made into relaxation oscillators. And so lots of people study what happens under the coupling of relaxation oscillators and so on. There's a whole field of excitable media that arises from studying things like uterine contractions, which Sitabra studies, or cardiac tissue, where a lot of people study how the heart functions and so on. And so reaction diffusion systems intersect very well with studying excitable media. Lots of people write down reaction diffusion equations for excitable media and study what the properties of those are. So there's a huge field, and I hope I've covered a small portion of it, and to whet your appetite. And maybe some of these ideas you can take over to other aspects of mathematical biology as well. If there's any questions, we can go to T and answer them, and at any point else.
So, how can we save these diagrams in ETS format?
Okay. File, PostScript. Yeah, you do a PostScript, it'll be able to save it.
So do you have to have the PostScript software in my...
XP will do it for you. You have to have the PostScript software to read it. If you need Ghost View or Ghost Script or something. or Illustrator, any of those. Okay, so thank you for the lectures, and we'll come back tomorrow doing some of these things in the tutorials, and hopefully they'll give you a sense of the basic ideas that are there, which you can then go on to develop in more careful detail on your own. Right? Thanks.